It's a pleasure to be here. It's a really amazing turnout, everyone here to hear about the neutrino. Today I'm going to be talking about one of our fundamental particles in particle physics called the neutrino. Specifically, I'm going to be focusing on how we can take pictures of this ghostly particle. So I sort of want to be upfront with you right away and tell you what I want you to take home from this talk. Okay, I'm going to be talking a lot about neutrinos. You may not remember everything, but these are sort of the 5 things I want you to take home with you. The themes of my talk. I'll talk about each of these. So first, I want you to know that whenever anything cool happens in the universe, the neutrino is usually involved. And this is really the main reason I'm interested in the neutrino. I also want to get across that neutrinos are very surprising. Really, most, if not all, of the biggest discoveries within neutrino physics have been unexpected. Okay? Studying neutrinos can help us understand how the universe evolved from the first few moments after the Big Bang till today. And one of the things I want you to take home with you is that there's actually this sort of invisible world all around us. You know, there are invisible particles zipping around us as we speak. Some of these interact with our bodies, some don't. And in order to study neutrinos, we need a big and high-resolution camera or detector. Okay, so these are the themes of my talk. This is what I want you to take home. So before actually telling you what a neutrino is, I want to tell you about some cool things in the universe and how the neutrino is involved. Okay? So this is one of my favorite quotes about neutrinos. Whenever anything cool happens in the universe, neutrinos are usually involved. Okay. So stellar fusion. This is one of the most important processes to us. This is how the sun shines, how all stars shine. And neutrinos are produced in fusion reactions that occur inside of stars. And not only that, but we can actually detect these solar neutrinos on Earth, and therefore develop a picture of how this fusion process actually occurs. Okay, so neutrinos provide a window onto how our sun and all stars shine. Core collapse supernova, so when a big star reaches the end of its life and it runs out of fuel to burn, radiation pressure stops pushing outward and gravity takes over and the star implodes and then explodes. Okay? This is a very important process. Well, it's a very bright event. This supernova explosion is incredibly bright. It can be brighter than the entire galaxy that it's in for a very short amount of time. And despite that enormous light output from one of these stellar explosions, in fact, about 99% of the energy associated with that explosion actually comes out in the form of neutrinos. Okay? You should really care about core collapse supernova. This is how the universe produces heavy elements beyond iron. So your gold watch, all the heavy elements in your body, the heavy elements in your iPhone are produced in these stellar explosions. And neutrinos are thought to drive the explosion mechanism. And further, just like in the case of the sun, neutrinos detected from a supernova explosion can provide a window onto how the process actually proceeds. This actually isn't a supernova, it's a supernova remnant, so it's the sort of the gas left over after a star explodes. Neutrinos are very important as well for how the large-scale structure of the universe was formed. Okay, so here's an image of sort of the galaxies near us. We are at the center of this image. The angle represents the sort of place on the sky, and then the distance from the center represents the distance from us. And each dot represents a galaxy. Okay? So you can see that, in fact, the galaxies in the universe are not randomly distributed. Okay? There's actually structure here. You can see this sort of filamentary structure. And the neutrino, really the mass of the neutrino is thought to contribute to this gravitational clustering of galaxies, which set how the universe at the biggest scales, how the structure was set. Okay. The neutrino is actually also thought to be partially responsible for why the universe is made out of matter. Okay, why there's something in the universe rather than nothing. In the hot Big Bang, we actually expect equal parts of matter and antimatter to be produced, and we actually expect the matter and antimatter to annihilate to produce a radiation-dominated universe. We don't see a radiation-dominated universe. Luckily for us, we have a universe with stuff in it. And it's thought that perhaps a difference between matter neutrinos and antimatter neutrinos led to this, asymmetry that we see today. Neutrinos can also provide a window onto the Big Bang. There's actually 339 neutrinos produced in the Big Bang per cubic centimeter in the universe, in this room as well. And those neutrinos, once we figure out a way to detect them, we haven't been able to yet, but those windows can actually provide a window onto 3 seconds after the Big Bang. And of course, everyone in this room should care very much about the Big Bang, because without the Big Bang, we wouldn't have the Big Bang Theory television show on CBS. Okay, so what is a neutrino? Stepping back a little bit. So the two main things to know about the neutrino actually can be seen in its name. Okay, this is an Italian name, the neutrino. So you can see little, ino, and neutral. Okay, so the neutrino is little. It's one of our fundamental particles. We think of it as a point particle. There's nothing smaller. And then the neutrino is neutral in charge. Okay, protons have a positive charge. Electrons have a negative charge. Neutrinos, like the neutron, are neutral. And since neutrinos are neutral, this is partially responsible for another important fact about neutrinos, which is that neutrinos very rarely interact with matter. They very rarely hit anything. Okay? So in fact, I mentioned that neutrinos are produced in the fusion reactions inside of the sun. Those neutrinos make it out of the sun, and they're actually passing through our bodies as we speak. Okay, in the past second, 65 billion solar neutrinos coming from the core of the sun pass through your thumbnail. Okay? This is also true at night. I know it's daytime, so the sun is right there, but this is also true at night. The neutrinos make it all the way out of the sun, all the way through the Earth, and just pass through our bodies, don't hit anything whatsoever. And despite this enormous number of solar neutrinos passing through our bodies as we speak, only about 1 or 2 are expected to interact with our bodies in our lifetime. So clearly the neutrino doesn't really directly affect our lives, our daily lives very much. But we're very interested in its properties because it contributed enormously to the evolution of the universe. Like I said before, whenever anything cool happens in the universe, the neutrino is involved, and we want to understand the universe and the cool things, and to do that we need to understand the neutrino. Okay, so here's a table of our elementary particles within the standard model of particle physics. We have our quarks on top. Okay, neutrons and protons are made out of mainly up and down quarks. So there's up, charm, top, down, strange, and bottom. Up and down are really the main ones that are stable, and like I said, they make up neutrons and protons. Down here we have the familiar electron, which is an important part of atoms. Then here we have a muon and a tau. These are sort of the heavier cousins of the electron. In the middle we have our force carriers. These are the particles which carry force. So the photon is thought to carry the electromagnetic force. This is the force that keeps me from falling through the ground. It directs how molecules bind together. The gluon carries the strong nuclear force. This is the force responsible for holding the nucleus together, keeps the protons and neutrons from flying apart. And then we have the W and Z bosons, which carry the weak nuclear force, which is responsible for radioactive decays. Okay? And last but not least, we have our 3 types or flavors of neutrino. Okay? So we have an electron neutrino, a muon neutrino, and a tau neutrino. And each of these, as you can tell, are sort of associated with one of the charged leptons, we call them over here. So electron neutrino goes with the electron, muon neutrino goes with the muon, tau neutrino goes with the tau. Okay, so what does a neutrino look like? So neutrinos are like, this big, they're yellow, they wear this bandit's mask. So what does a neutrino really look like? So, arguably no one's ever sort of directly seen a neutrino, in much the same way that no one's ever really seen a neutron. Okay? But what we see is what happens when a neutrino interacts. When a neutrino hits something, we can see the particles that are produced and therefore infer properties of the neutrino itself. Okay? So here's an example of what a neutrino, a fairly energetic neutrino interaction looks like. So this is a detector that was about this big, okay? And we put this detector in a neutrino beam. And as you can see, a neutrino comes in from the left. It doesn't leave any trail. It hits literally nothing on its way through this detector. And then suddenly, it interacts with a nucleus. It hit an argon nucleus in this case. And you can see that that interaction basically exploded the nucleus. Okay, you can see a couple protons coming out. And this neutrino actually produced a muon as well, which was this guy right here. Okay? So this is what happens when a neutrino hits a nucleus. It basically creates charged particle shrapnel. Okay? And by reconstructing that shrapnel, we can infer properties of the neutrino itself. Okay, so neutrinos come in three flavors, like I said before. There's electron type or flavor, there's muon, and tau. And the idea is that when an X is produced, an X neutrino comes with it. Okay, so here I'm showing an example of what we call a beta decay, which is where a neutron turns into a proton. We have an electron which conserves the electric charge. We start with a neutral charge, we end up with a neutral charge over here. So a neutron decays into a proton and electron, and then we get an electron neutrino, which comes with that electron. Okay? So when an electron is produced, an electron neutrino comes with it. Similarly, when an X flavor neutrino interacts, it produces an X. Okay, so if an electron neutrino were to interact with a neutron, for example, inside of a nucleus, it would produce an electron. Okay? A muon neutrino will produce a muon, and a tau neutrino would produce a tau. So that's the idea behind the three types or flavors of neutrinos that we have. One of the biggest discoveries in the past 20 years or so within particle physics is that neutrinos actually mix, or some people say neutrinos oscillate. I think oscillate is too fancy of a word. I like mix. Okay? So the idea is that a neutrino created as one flavor can actually change into another flavor after traveling a distance. Okay, so the idea is that you can create, for example, a muon neutrino and observe that originally muon neutrino as an electron neutrino sometime later. And so this means that the neutrino changes without any external force or anything. Okay? So the key word is change. The neutrino feels time, it experiences time. And so unlike the massless photon, the neutrino has a mass. And this is a really big deal because the neutrino was originally conceived as a massless particle. And it's also a big deal because neutrinos outnumber electrons, protons, and neutrons by a factor of 10 to the 10 in today's universe. Okay? There's 1 followed by 10 zeros times more neutrinos than there are electrons, protons, and neutrons in today's universe. And when you give this particle that was originally thought to be massless a mass, it changes things. Right? It changes our interpretation of the universe. Okay, so how does this mixing work? How does one neutrino change into another? The idea is that every neutrino, as it's traveling along, is in a superposition of wave states. Okay, it's a quantum mechanical process, but it's very easy to understand. The idea is that every neutrino is in a superposition of wave states, and the waves that make up the neutrino interfere with each other, and this interference can cause a neutrino to change its flavor after traveling. It's sort of like if you add two slightly different frequency waves together, you get beats. Okay? So here's my first demo over here. So we have two tuning forks right here. One is at 109 hertz. So you can see the nice sine wave associated with this frequency on the oscilloscope. Okay. One is at 108 hertz. Sounds about the same. Slightly different. Okay. But when you hit them both together, we get beats. See that wah, wah, wah. So it's very similar to what happens in neutrino mixing. Okay? Instead of adding two sound waves together to get this beat behavior, okay, we have two wave functions that make up the neutrino that, as the neutrino is traveling, interfere with each other, and it causes the neutrino flavor to mix. Okay? And the beats in the neutrino case correspond to, for example, the probability of detecting an originally muon neutrino as an electron neutrino is originally 0, and then the probability to detect an electron neutrino from that originally muon neutrino increases. Okay, and then it goes back down. So it's very similar to how neutrinos mix. And this discovery that neutrinos mix and therefore have a mass is responsible for our most recent Nobel Prize in physics, which was announced in October 2015. And it was given to these two guys, which led big experiments which established that neutrinos mix. I'm not going to really go into their experiments in detail, but I did want to tell you about Kajita-san's experiment because I think it illustrates how neutrinos are very surprising. Okay? So let me briefly tell you about the story of Kamiokonde. So the Kamioka nucleon decay experiment, Kamioka is a small town in the western side of the main island, Honshu, of Japan. So this experiment was erected in the early 1980s in Japan, and the goal of this experiment, as you can tell from the name, was to observe nucleon decay, to observe the decay of a proton using a large water-based detector. When a proton decays, it's thought that it produces a characteristic flash of light, and that's what this experiment was looking for. It took data for a long time. An upgraded iteration of it is actually still taking data as we speak. And unfortunately, the decay of the proton was never seen. Okay? And it still hasn't been seen after taking data for 25 some years. However, the experiment and subsequent upgrades of this experiment ended up winning 2 Nobel Prizes in physics. And that is absolutely extraordinary. Okay? I don't think I'm aware of any other experiment that has won 2 Nobel Prizes in physics. And both of these discoveries, which led to these 2 Nobel Prizes, had to do with neutrinos and were completely unexpected. They were big surprises. Okay? So one of the Nobel Prizes was given for the unexpected discovery of cosmic neutrinos produced in a supernova that went off in 1987 in the Large Magellanic Cloud, one of our neighboring galaxies. Here's a sort of before and after picture of the supernova. So this experiment, Kamiokonde, detected about 10 neutrinos which were produced in this stellar explosion. And that won a Nobel Prize. And then another Nobel Prize was given for the unexpected discovery of neutrino mixing and mass, and that was the most recent Nobel Prize. And this is incredibly ironic, right? This is the Kamioka nucleon decay experiment. They never saw nucleon decay, but they ended up winning 2 Nobel Prizes for completely unexpected discoveries. And I should tell you that they were smart and changed their name to the Kamioka neutrino detector experiment. And this is actually the latest version of the experiment. It's called Super Kamiokonde now. It's a much bigger detector than the original one. It's a very large volume, I think 50 kilotons or so of water surrounded on all sides by these light detecting devices. And just for scale, this is a raft with people on it. Okay, so back to our main line of the talk. So neutrinos have mass. So what? What does that mean? Why should I care? So one of the misconceptions I think about what particle physicists do is that we don't tabulate the properties of the particles for eventual entry into a big dusty catalog that sits on a shelf somewhere. We're not stamp collectors. Not that there's anything wrong with that. But the job of the particle physicist is to measure the properties of these particles in the lab and relate them to the big questions. The biggest questions, why are we here? How was the universe created? How was the universe formed? So the job of the particle physicist is to measure the properties of these particles and then relate them to the big questions in astrophysics and cosmology. And the idea behind studying the neutrino is that we want to elucidate the nature of the neutrino mass. We want to measure the mass of the neutrino, which we actually don't know. We want to understand how the neutrino got its mass. and we want to understand how the neutrino mixes, and those things can tell us about how the universe evolved. So we want to relate the smallest scale to the biggest scale. Okay. So neutrino mixing is a big deal. Like I said, neutrinos are extremely prevalent in the universe. When you give this particle a mass, it has a big effect on things. And I sort of list a number of topics where neutrino mass and mixing is relevant. So neutrino mass and mixing is very important for understanding Big Bang cosmology, how the universe evolved from the earliest moments. It affects cosmic observables. It can tell us perhaps why the universe is made out of matter versus antimatter. Neutrino mass and mixing provides a window onto how supernova, these stellar explosions, evolve, and therefore how heavy elements are produced in the universe. Neutrino mixing can help us understand how the sun shines and how nuclear reactors burn fuel. And there are many other questions within particle and astroparticle physics that this process can help us understand. So we know neutrinos mix. We know this process happens, where you have an originally muon neutrino, and then it can be detected sometime later as an electron neutrino. And our job now is to really precisely measure this process, determining how often it happens and under what circumstances. Okay? And answering these questions can provide insight into two of the biggest questions that we have. So we sort of went over this one briefly before. So the big question is, why do we live in a universe made out of matter? So what we see all around us, everything in this room is made out of matter. When we look through our telescopes, most of the cosmic objects, really 99.9 something percent of the cosmos that we observe seems to be made out of matter. And we do see a small fraction of antimatter in the cosmos, and we are able to produce antimatter in particle accelerators, but it's not clear why we don't live in a universe with 50% matter and 50% antimatter. And equivalently, we're actually not sure why we don't live in a radiation-dominated universe, because we actually expect matter and antimatter to annihilate to produce radiation. So this is what we see. We have a universe with stuff in it. This is what we actually expect to see. And so the idea is that perhaps there's some fundamental difference between matter and antimatter, which led to our universe being made out of matter. And so the related question in neutrino physics is, do matter neutrinos and antimatter neutrinos mix in the same way? And can this tell us about this big question at the top? Another big question is, why do galaxies clump? Why do we see this structure of galaxies? Okay? And the related question in terms of neutrino mass and mixing is, what is the neutrino mass? And how is the mass distributed across the three types of neutrinos? And yeah. Okay, so how do we do it? How do we study neutrino mixing in order to answer these big questions? So studying neutrino mixing is actually a fairly simple process when it comes down to it. Okay? These experiments take a long time, and there are many people involved, and the experiments tend to cost millions, if not billions of dollars. But when it comes down to it, all we do is make a lot of neutrinos and then count them, okay, to see if they're changing, to see how they mix. Okay? First, of course, we have to decide what we want to measure before we can set up our experiment. So let's talk about number one briefly. So we want to answer these big questions. Okay, do matter neutrinos and antimatter neutrinos mix in the same way? And then how is the neutrino mass distributed across the three types of neutrinos? And to answer these questions, what we do is, like I said, we make a lot of neutrinos and then we count them. Okay, this is how we do that. We take a beam of originally muon neutrinos and we shoot them at a set of detectors. Okay, we sample this beam as a function of distance and time. And we see if these originally muon neutrinos are turning into, for example, electron neutrinos. So we sample the beam at very close to the time where the neutrino is created, because the neutrino needs time to be able to mix. And so we sample the beam at what's called a near detector, which is typically hundreds of meters away from where the neutrino is created. And then we actually point this neutrino beam into the Earth. Okay, there's no tunnel or anything. The neutrinos pass right through. And then where the neutrinos come out of the Earth, near the surface, we place a far detector, okay, which tends to be hundreds of kilometers, actually over 1,000 kilometers in some cases, away from where we created the neutrino, okay, in order to see if these muon neutrinos are changing into electron neutrinos. And then what we do is we actually make a beam of antimatter neutrinos and ask the very same questions. Okay, are these antimatter muon type neutrinos turning into antimatter electron type neutrinos? And then we ask the question, is matter behaving the same as antimatter? Okay. And if they're not, if we actually find a difference between how matter neutrinos behave and how antimatter neutrinos behave, then we may actually be able to say something about why the universe is made out of matter. Okay. So I'm actually going to skip that slide. Okay. Step 2 is we make a lot of neutrinos. Okay, we need to create this beam of neutrinos in order to characterize it. So let's talk about how we do that. Okay. So neutrinos are expensive. This is one of the important things to remember. $10.49 plus shipping. In reality, neutrinos actually are expensive. Particle accelerators are expensive, and so thank you, taxpayers, for helping us build this. This is a Department of Energy National Lab. This is 4 hours and 15-minute drive away from here. It's about 40 minutes west of Chicago in Batavia, Illinois. It was a sort of a hazy day when this picture was taken, but if it wasn't hazy, you might be able to see the Chicago skyline sort of over here. But anyway, this is Fermilab. This is home to, or it used to be home to the highest energy particle accelerator in the world before it was surpassed by the LHC in Europe recently. And that accelerator was the Tevatron, which is here, which is now decommissioned. But there are 2 neutrino beams created by these particle accelerators at Fermilab. Okay, so Fermilab, by the way, is a proton accelerator complex. These machines are used to accelerate protons to very high energies. Okay, so one of the neutrino beams utilizes this accelerator right here. This is called the main injector. And then one of the neutrino beams is created from this accelerator over here, which is called the booster. Okay. So how do we create a neutrino beam? This is also a pretty simple thing. So you take these beams of protons, accelerated to high energies in these particle accelerators, and you shoot the beam of protons onto a target. Okay, a target is not complicated at all. It's sort of like a cylinder like this. It's a big piece of graphite. Okay, the protons hit one end of the target. It's a very energetic interaction, and so many particles are produced in this proton on target interaction. And the particles we're interested in are called pions. Okay? A pion is a combination of up and down quarks. And it's unstable, so the pion, as it's flying, can decay into a neutrino. Okay? So we end up producing a beam of neutrinos by creating these particles called pions. And one of the nice things about pions, these pies I'm showing here, is that they're charged. Okay? And we can take advantage of that fact and use an electromagnet, which we call a horn, to focus the pions, the charged pions, down the beam line. And then we let the pions decay and they produce a nice beam of neutrinos. So that's how we do it. We take protons, they hit a target, we produce pions, we focus the pions down the beam line, we end up with a beam of neutrinos. Then what we can do is we can actually change the direction of current in our electromagnet to focus negative pions instead of positive pions. The nice thing about negative pions is they decay into antimatter neutrinos instead of matter neutrinos. So this is a wonderful technique if you want to compare how matter neutrinos are behaving to how antimatter neutrinos are behaving. Okay. So this is a little more detail about how it works. We have a proton beam hitting this target. There's a target, it's a little hard to see. The target is inside of this electromagnet, which we call a horn. It's about this big, to give you a sense of scale. And the protons hit the upstream end of this target, and they produce pions. These red lines are pions in this picture. You can see that they're sort of focused down the beam line by this electromagnet. And then we actually instrument a second and third electromagnet, which literally act as charged particle optics. They focus these pions down the beam line into a nice tight beam, And then the pions decay into neutrinos. Neutrinos are neutral, remember, so we can't focus them using our electromagnets, but we focus the parent of the neutrino instead. And over here, I'm actually showing the antimatter neutrinos, or I'm sorry, I'm showing the pi minus, the negative pions defocused out of the beamline. So these are pi plus being focused, which gives you a nice beam of matter neutrinos, and the negative pions are being defocused out of the beam. Okay, so we have our technique of making a lot of neutrinos using a particle accelerator, and now we need to count them. Okay, we need to take pictures of our neutrinos to see if they're mixing, how often they're mixing, and how it works. Okay. The key to studying neutrinos, in terms of taking pictures of neutrinos, is that you need a really big detector. And you need a detector that's capable of measuring the flavor and energy of neutrinos. You obviously need a big detector because neutrinos so rarely interact. Okay, you want to detect, you want to collect and characterize a lot of them in order to be able to say something about them. But you also want a detector that's capable of measuring the flavor and energy of neutrinos. Okay? If you want to say something about how muon type or flavor neutrinos change into electron type neutrinos, then you better have a detector that's capable of measuring the flavor of your neutrinos. And further, the mixing process is a function of how far the neutrino travels and its energy. So you also want to be able to measure the energy. So I want to give you sort of a quantitative feel about these experiments, how big they are, how many neutrinos they detect. So there's an experiment called NOVA. It's one of the premier neutrino mixing experiments in the world. It features a 14,000-ton FAR detector, which samples the beam, the neutrino beam, after it's traveled a very long distance. So here's the 14,000-ton, actually both of these pictures show the 14,000-ton NOVA detector. There's a person over here to give you a sense of scale. Very big detector, very big neutrino camera. And the idea is that a beam at Fermilab in eastern Illinois, this particle accelerator complex at Fermilab produces a beam of neutrinos, shoots it into the Earth, and then when it peaks out of the Earth in northern Minnesota, in Ash River, Minnesota, this detector samples it. Okay, samples that beam of neutrinos in order to see how these neutrinos mix as a function of how far they travel and their energy. Okay, so this is the world's most powerful beam of neutrinos currently. It's a gigantic detector, and unfortunately, the detector only sees about 1 electron neutrino per month. Okay, and we want to collect a lot of events in order to be able to describe this mixing process, and 1 electron neutrino per month may not be enough. So this is a fairly simple concept, but I want to talk about why we need to collect a lot of neutrinos. Okay, so say I'm trying to determine if there's a difference between how matter neutrinos mix and how antimatter neutrinos mix. So I start with a beam, or really 2 beams, equal parts matter muon neutrinos and antimatter muon neutrinos. And say, just as an example, at my detector, I observe 8 matter electron neutrinos from this originally muon neutrino source. And then I observe 6 antimatter electron neutrinos from my originally antimatter source. And the question is there a difference between how matter and antimatter neutrinos behave? I've seen more matter neutrinos than I've seen antimatter neutrinos, so does that mean that there is a difference between matter and antimatter? And of course the answer is, I don't know, I didn't collect enough events. Okay, so this is what we call a statistical error in physics. We have to collect enough samples to be able to say something intelligent. Okay, and this is really similar to polling. Okay, the election is on our minds, polling is on our minds. The goal of the pollster is to contact as many people as possible to try to figure out who will win an election. And in general, the more people polled, the better. Okay, but it's not just that. It's not just that the more people polled, the better, because you can't poll everyone. And so what the pollster does is they try to poll a representative group of people, and then they try to correct for any biases or perceived effects using a model. Okay, and this can introduce what we call a systematic error on the measurement. So this is called a statistical error. You know, the more people polled, the better. The more neutrinos you collect, the better. And then down here, we have a systematic error, a source of systematic uncertainty. So I'm going to show results from the 2016 Democratic primary election. And so this is the Clinton versus Sanders, obviously. This is the actual margin of victory. This is as of 2 weeks ago when I started preparing. And this is the prediction from the polls. This is from Nate Silver's blog. So this is the prediction for how much Clinton would beat Sanders. Okay, in Michigan, as you may recall, Clinton was predicted to beat Bernie Sanders by 24% in the Democratic primary election, but Bernie Sanders won by a few percent. Okay. So this is a really nice example of a systematic error, systematic uncertainty in polling. Okay? And we deal with these same sorts of issues in particle physics. Okay? We don't just need to we don't just need to collect a lot of neutrinos, we need to be able to characterize them, and we need to have models which can help us do that. Okay, there's some, of course, explanations for why the predictions got it so wrong. Okay, so here's another sort of, to drive this point home, you know, we have a picture of a lion neutrino here, as you can see. And so the question is, you know, why do we need to take high-resolution pictures of our neutrinos? You know, so we can rely on models, just like the pollsters rely on, to enhance or interpret our results, our pictures, or, you know, we can just take a better picture. Okay. It's actually a cat neutrino. Okay, so that's why we need to have a big neutrino detector, and we need to have a capable neutrino detector which can provide high-resolution images. Okay, so let me talk about how we take pictures of particles. So luckily, there are particles streaming all around us as we speak. And so I can actually show you how we take pictures of particles in real time. So the idea is that when a particle travels through a medium, a detection medium, for example, it ionizes atoms along the way. Okay, it excites atoms, and the atoms lose an electron. So here I'm showing how an argon atom can lose an electron. And the idea is that we can actually try to detect this ionization created when a charged particle excites an atom. Or we can actually try to detect the light produced when either the electron and ion recombine to produce an excited atom. Or we can, you know, directly detect the light produced from the de-excitation of the original ion. Okay? So the idea is simply that we can try to, trying to take pictures of particles, we can detect the charge, you know, the electron produced when a charged particle excites it, or we can detect the light produced. Okay? So I have to push something? No, I don't. I do have to push something. Yes, okay. So over here we have, this is a particle detector. This is what's called a muon telescope. Okay, so like I said, you know, this incredible thing is that there are these invisible particles streaming all over us as we speak, hitting our bodies, ionizing atoms in our bodies some of the time. And the idea is that, you know, these particles, called cosmic rays, originate in cosmic collisions, and they rain down on Earth, and they interact with the Earth's atmosphere, and that creates more particles, and these particles reach us in this room. And there are particles streaming down in this invisible space as we speak. We can't see them, but they're there. And so the idea is we have a sort of piece of plastic called a plastic scintillator. It just means it's a piece of plastic that sort of lights up when a charged particle passes through it in this way. Although it's not an argon atom, it's a carbon or hydrogen atom. And so it produces a lot of light when a charged particle passes through it. And then we have these sort of electronic eyeballs, which are called photomultiplier tubes, here and, I guess that one's not plugged in, right here, which creates a signal associated with when light is produced. Okay, so the top signal is shown in yellow, and then we have the same thing down here. This is the blue signal. Okay, so when we hear this noise, when we see a coincidence of events, that means that a charged particle has created light in this detector and then created light in this detector in a very short amount of time. Okay, so this is a nice charged particle detector. I think it's just incredible that there are just particles streaming through here. We can't see them, but they're there. Okay, then we have another particle detector, which is called a cloud chamber. Yes, so see those tracks? Those are all particles that are interacting. Okay, so the idea is we have a volume of alcohol vapor. It's kept very cold, and so the idea is that the alcohol vapor wants to condense. It wants to turn into a liquid. And it can't really do so nominally. But what happens is when a charged particle travels through this medium, it creates ions. Okay, it excites atoms, and you're left with electrons and ions. And it gives the vapor a medium onto which it can condense. Okay, it's sort of like blades of grass provide a medium onto which water vapor can condense in the early morning. Right? So that's a very similar idea to what's going on here. In the middle, there is a rod that contains thorium, which is radioactive, which emits alpha particles. Alpha particles are just helium nuclei. And so if you see particles emanating in the radial direction from the rod, those are alpha particles produced from radioactive decays in the rod. Okay, so these sort of radial ones are alpha particles. And then this detector is also sensitive to these cosmic ray particles, which are showering down on us as we speak. Okay, so these two techniques are ways in which we can detect charged particles. They represent ways in which we can take pictures of the subatomic, these subatomic particles. Okay. So yeah, here's the idea of the cloud chamber. We have an energetic charged particle traveling through this medium, and it leaves these trails of electrons and ions in its wake. And it's usually very hard to see. We can't see them with our eyes very easily. And so the trick behind how particle detectors work is they sort of allow us to see the events using various tricks or amplification techniques. Okay. Okay, so I wanted to sort of make sort of a philosophical slide. I think this is a really amazing thing, that there's this sort of invisible world happening all around us. This is one of the themes of science. Okay. So not only are we traveling on this tiny rock in the vast and possibly infinite universe, traveling at these enormous speeds, with bodies made of stardust, our senses, which we rely on enormously to form our intuition in combination with our brain, are extremely limited. Okay, we can't really see what's going on around us. In fact, we only realized that there was such a thing as cosmic rays, as these particles streaming down on us all the time, in 1912. Okay, so we know how to build a high-resolution particle detector. I've shown you a few examples of fairly high-resolution particle detectors. The problem is that we need a neutrino detector to not only be high-resolution, we want it to be gigantic, okay, and cost-effective. So let me tell you about sort of the best way we know of right now to take pictures of neutrinos. So this is something called a liquid argon time projection chamber. It's way too complicated of a name, in my opinion. It's actually not that complicated at all. So the idea is we have a volume of liquid argon. Argon is a liquid at 87 Kelvin. It's very similar to liquid nitrogen. So we have a volume of liquid argon. And the idea is that a neutrino comes in from the left, as you can see here, and interacts with an argon nucleus, for example. And this interaction causes charged particles to be produced. And as these charged particles travel through the argon medium, they excite atoms and leave a trail of electrons and ions in their wake. Okay? So what we do is we impose an electric field in this volume, which means we just drift, we force the charged particles in a certain direction. So we drift these charged particle-induced tracks to a set of wire planes. So a wire plane looks like this. It's sort of just a plane of parallel wires separated by a few millimeters. Okay, this is actually a picture of 3 wire planes. Here's what sort of liquid argon looks like. It's a very boring, clear liquid that's very cold. Okay, so we have this neutrino. It interacts. It produces these charged particle tracks. We really want to know what these charged particle tracks look like because it allows us to infer properties of the neutrino itself. And we drift these electrons up to a set of wire planes. And the wire planes basically provide a 2-dimensional projected image of the neutrino event. And then we collect the event in time as well, and that provides the 3rd dimension. So combining all this information together in terms of time and wire number on one of the wire planes, and then time and wire number on the other wire plane, we can create a 3-dimensional picture of this neutrino event. Okay. So here's sort of the world's foremost liquid argon time projection chamber. This is an experiment I'm a part of. It's called microboon. It's currently sitting in a neutrino beamline at Fermilab, taking data as we speak. It's about 170 tons of liquid argon. Here's a picture of our leaders, the experimental leaders. And here's one of the neutrino pictures we have captured. Okay, so this is a picture taken with this neutrino camera using this liquid argon neutrino detection technique. So the idea is that, once again, a neutrino comes in from the left, interacts, and produces this sort of charged particle shrapnel. Okay. So this is one of the sort of best pictures of a neutrino we have. Also, interestingly, you can see a number of other sort of straight line tracks, and I'm sure you can guess what those are. Those are cosmic ray muons, the same particles that were traveling, legging up the particle detector over there. Here's a few more examples of neutrino events that we have taken with this experiment. Here's from the left, a neutrino comes in, interacts right here, and produces these charged particle tracks. These little dots right here are actually photons which come from the nuclear excitation of this neutrino, occurring from this neutrino event. So when the neutrino comes in, not only does it produce these charged particle tracks, but you're left with an excited nucleus, which then de-excites and gives off light, gives off photons, and that's what these little dots are. Here's another nice sort of V-shaped neutrino event. Neutrino came in and interacted right here and produced these charged particle tracks. Okay, so we are, the US high energy physics program is building up, and we are trying to build a 40,000 ton liquid argon device. Okay, this microboon experiment, this is the biggest liquid argon neutrino detector in the US, and we're actually trying to build one that is about 1,000 times bigger. Okay, we plan to put this detector deep underground in South Dakota, okay, in an old mine in South Dakota. And the idea is we want to take a neutrino beam produced at Fermilab over here in Illinois, shoot it underground, and then capture these neutrinos and see how they mix in South Dakota. Okay? And this experiment will be able to answer these 2 big questions in particle physics and cosmology. Do matter neutrinos and antimatter neutrinos mix in the same way? And how is the neutrino mass distributed across the 3 types of neutrinos? And I should say that we have some competition. Okay? So astrophysicists using telescope-based measurements are actually closing in on a similar question. What is the mass of the neutrino, and how is the neutrino mass distributed across the 3 types of neutrinos? So here's a numerical simulation of sort of the large-scale structure of the universe. Okay? You can see there are 2 cases. So the density distribution of galaxies in the universe is shown on the left with massive neutrinos, and on the right it's shown without massive neutrinos. So in fact, looking at the large-scale structure of the universe, how galaxies have clumped together, provides a measurement of the neutrino mass and how the neutrino mass is distributed across the 3 types of neutrinos. And that is totally extraordinary to me, right? We have a particle physics experiment on Earth that takes a particle accelerator, creates a beam of neutrinos, and then detects it using a liquid argon device. And that can tell us about a property of neutrinos. And then we can measure the same property of neutrinos looking at the largest scale, using telescopes. Okay, and that's what's called astroparticle physics. Relating the smallest scale, the particle physics scale, to the biggest scale, the universal scale. Okay, so that's about it for my talk. I wanted to sort of remind you of the themes, what I want you to take home. So whenever anything cool happens in the universe, the neutrino is usually involved. Neutrinos are surprising. Basically, every big discovery in neutrino physics has been unexpected. Studying neutrinos can help us understand how the universe evolved. There are these invisible particles zipping around us as we speak. Like I said, one of the themes of science is teaching us about these microscopic and macroscopic worlds which we just cannot sense with our five senses. And particle detectors are helping us gain a sense of the invisible world around us. And in order to study neutrinos, we need a big and high-resolution detector and a big particle accelerator. Okay? So I wanted to sort of end really trying to hammer this point home that neutrinos are surprising. Okay? And I would go so far as to say that neutrinos are laughing at us. Okay? I didn't really go through the history of the neutrino, but originally the neutrino was conceived as a bookkeeping device made to ensure conservation of energy and momentum. And it turns out that the neutrino is real, in fact. It's not a bookkeeping device, so we were wrong. And when people started to realize that the neutrino was probably actually a particle, most people said that the neutrino was completely undetectable. We'd never be able to detect it. And we were wrong once again. And this led to 2 Nobel Prizes, 1995 Nobel Prize for detecting neutrinos for the first time, which happened to occur at a reactor. And then the 2002 Nobel Prize for detecting cosmic neutrinos. And then we thought that there was only one type or flavor of neutrino. And we were wrong once again. Okay, and the 1988 Nobel Prize was given for the discovery of the muon neutrino. And then the standard model of particle physics was originally written down featuring a massless neutrino. So we thought the neutrino was massless, and we were wrong once again. And this led to our latest Nobel Prize in physics. So after 80 years, since the neutrino was first conceived, we think we understand the neutrino pretty well, but we're almost certainly wrong. So in 1960, John Updike wrote this poem, which was published in the New York Times. This is an abbreviated version. So neutrinos, they are very small. They have no charge and have no mass and do not interact at all. The Earth is just a silly ball to them, through which they simply pass and pierce the lover and his lass. So after 80 years, we think we understand the neutrino pretty well. We're almost certainly wrong, but as you can see, we are making progress. So thank you.